With 8.86, I think we kind of assume a few things. So a bullet is shot through a wooden block. First of all, let's draw a block and give it the mass m. And then here's a bullet. I'm going to draw it sort of far away from the block. I'll give that a mass little m and a velocity v. So this is before the collision. This will be right after the collision. So there's some interaction time as the bullet's going through the block. And so if I actually drew this right here, so that's really right before the collision. My velocity symbol is going to be in the way. So this is really right before the collision. This will be state A. And this will, I'm going to call this state C, because I am anticipating no, you know what? Just make this state. I'll just make it state B. That's still capital M. This is still M. We're assuming well, if you shoot something, there's debris, like pieces of wood will fly around. We're going to ignore all of that. So I guess one of the skills in doing these physics problems is to know what to assume and know what to ignore and know what to consider. So in a real world example, if you shoot a bullet through a block, that block is going to become more damaged than this problem. Right? In this problem, nothing happens really to the block except you put a hole in it. It's more like you push the wood out of the way of the bullet, but the block still holds that much weight or that much mass or that much wood. So the mass before the bullet collision will be the same as the masses after. The bullet's mass, though, is 5 grams. So that's 5 times 10 to the minus 3 kilograms. And the block is just 1 kilogram. The velocity or speed of the bullet, 450 meters per second. And one final thing, because of the interaction between the bullet and the block is going to swing out a little bit. The bullet's long gone. I'll draw it here, but I might as well have not drawn it at all. It doesn't matter for the rest of this problem. After this point, we don't care about the bullet. The speed of the bullet, once it exits here, what should I call? I'll call it U. The speed of that bullet is what we're looking for. That will be the same as this, we'll assume. Now the block rises in height a little bit. So we'll say that's the center here. The drawing isn't very good. But if I continue that line. This distance h that the block rises up is given. In the problem, it's given as 0.38 centimeters, so that's 0.38 times 10 to the minus 2 meters. Okay, so how do we figure this out? Well, what's between the two states A and B is an interaction between the bullets, or between the bullet and the block. That interaction conserves momentum. It doesn't conserve energy. I mean, it might conserve energy, but it's not guaranteed. Momentum, though, is guaranteed to be conserved. So in state A, all the momentum is in the bullet. So total momentum in the system is equal to the momentum of the bullet only. I could put this here for the block, but this is 0. The velocity of the block is 0 in state A. So system in state A, bullet in state A, block in state A. What is the momentum of the bullet? Little m, little v, I hat. Right after the collision, in state B, P total, the system, state B, we're going to have little m, u, I hat, but now the block is moving. I should have, let's see, I'll use light gray and a big arrow. And I'll call that big V. So that's big V also in the I hat direction. So you see the total momentum before the system, before the collision, is equal to something just in the x direction. After the collision, momentum's got to be conserved. So these two terms have to add up to this one term. Therefore, probably, and they're both going in the same direction, so neither of these terms is going to be as big as this one term, because the conservation says mv from this has to equal mu plus big M, big V. So the speed of the bullet after the collision is simply mv minus big M, big V divided by little mass, bullet mass. I can cancel the little m's here. So that term will be dimensionless. And it's just a ratio of mass over mass, so that the units go away. And now I have just... Okay, so everything's looking right. The only thing is I don't know what this big V is. And that's why the hint of the block rises a distance h. And that's just an energy conservation thing. So it had kinetic energy 1/2 big M, big V squared, getting transferred into gravitational potential energy. Look at that. M cancels on both sides. And based on the height that the block went up, I've got the speed of the block right after the collision. So use this result back down here. The speed of the bullet is the initial velocity of the bullet minus this ratio times square root of 2gh. Or 450 meters per second minus 1 divided by 5 times 10 to the minus 3 times the square root of 2 times 9.8 times 0.38 times 10 to the minus 2. e2 negative times 9.8 times 2. Take the square root, divide that by 5e to the negative, 5e3 negative. That's 54.582. So the speed of the bullet right after the collision is about 395 meters per second. Right, so to recap, we have three important figures right before the collision, right after the collision. The collision happened in between those two states. And then between B and C, there's energy conservation going on in the block. The block has an initial kinetic energy because of this velocity here, makes the block go up a distance h. So I can get the velocity of the block right after the collision based on the height the block went up using the conservation of energy on the block between the B and C, states B and C. That goes into an equation that conserves momentum between A and B. So here's the momentum in state A, here's the momentum in state B, composed of two pieces. I solve for the speed of the bullet right after the collision, so that's what the U is. So I take the the momentum conservation equation, solve for U, I get this result, or this result, sort of simplified, but then I can use my energy conservation result to rewrite the big V, and that's what this is. And then after that it's plug and chug, put in the numbers, and final bullet speed right there.